Okay, thank you. Thank you everybody for being here. Welcome to this session with Jan Stojka from the RISElab. My name is Jed Sonwall. You may have been here for the last session. I run the Open Data program at Amazon Web Services and work really closely with a lot of researchers and people who work with really large volumes of data in the cloud. Jan has been a visionary for a really long time, researching how distributed systems and cloud systems can be used to enable more sophisticated and much faster science and better made decisions. And so based on his work at UC Berkeley, now at the RISElab and building on the legacy from the AMP lab, he's here to talk about how the RISElab is using the cloud to enable intelligent real-time decisions. It's really spectacular work, and it's really an honor to have Jan here to speak with us today. So without further ado, please welcome Jan Stojka from RISElab.
Thank you. Hello, everybody. It's a pleasure to be here, and thanks for coming to attend the talk. So today I'm going to talk about this new lab we are starting at Berkeley called RISElab. But before, let me tell you a few more things about me. So I am RISElab director. I am a faculty at UC Berkeley, and I've been also co-director of AMP Lab. In the other life, I am also co-founder and executive chairman of the Databricks, which is providing a unified analytics platform on AWS around Apache Spark. And I'm also co-founder and CTO of Conviva, a video analytics company. So first, let me tell you a few words about the AMP Lab. The AMP Lab was a previous lab at Berkeley, or project, and it was duration is between 2011 and 2016. At Berkeley, the labs typically have a duration around 5 years. Each lab has a particular vision and a particular goal. In the case of the AMP Lab, the mission was to make sense of the big data, and the approach was to use a holistic solution consisting of algorithms like machine learning, machines, that is systems, and people, or crowdsourcing. It included over 8 faculties and over 60 students, and it has a broad government and industry support, including Amazon, AWS. And we are lucky we had quite a bit of impact with AMP Lab. On industry, we created and pushed out Apache Spark. How many of you use or know about Apache Spark? Okay, thank you. So today, there are over 1,000 customers, or thousands of customers. Is a de facto big data processing engine today. And around the globe, in terms of the Meta members, has close to 400,000 today. Besides Apache Spark, we release Apache Mesos. Hundreds of customers we have with on Apache Mesos and Alusio in memory storage engine. Apache Mesos, it's a cluster management, allows you to run multiple frameworks and share the same cluster. Out of those projects, we've been created 3 startups. They raised, on aggregate, well over $200 million. And also, we are, a university. So also, we are very proud about our academic impact. Alumni from AMP Lab went to become faculties at MIT, Stanford, Carnegie Mellon, Cornell, University of Michigan, and so forth. We also won, among the alumni, 3 ACM Dissertation Awards, which is the highest distinction for thesis across the world every year. Okay, so with AMP Lab, we leverage AWS from day one. We started again in around 2011. AWS was still kind of at the beginning, but we went all in. And actually, AWS was the first cloud to host Apache Spark, starting to 2013. We also use AWS to beat the TerraSort record in 2014. The TerraSort record, it's the TerraSort benchmark. It's a benchmark to sort 100 terabytes of data, and it's for big data frameworks. And in 2014, again, we use AWS. And the preview, just to give you a sense, a previous record was in 2013 was Hadoop and run on 2,000 machines. It was a Yahoo cluster, and it took 72 minutes. In 2014, on we use Spark, and it's again, there are kind of different machines, but still, we used only 200 machines in Amazon, pretty beefy machines, I should say, and it took only 23 minutes. Actually, it was linearly scalable because when we went to 1 petabyte, it took us only 4 hours. So the difference between 1 petabyte and 100 terabytes is, of course, a factor of 10. So if you multiply, the 23 minutes by 10, you get 230 minutes, so it's approximately 4 hours. Okay, and we are capped actually by the network capacity of 10 gigabits per second. So it's again a lot of work in the area of big data, a lot of work we've done on AWS. So now AMLab is done, so the next lab we've been started is RISElab. Now to put them in context, think about AMLab of building analytics tools and systems to perform advanced analytics on batch data. In contrast, RISElab is about providing real-time decisions on live data, and I'm going to give a motivations why we are excited about this. But before, RISElab includes an ensemble of faculties across systems, security, AI, and system architectures. And it's also funded by 11 funding sponsors, including AWS. So why we are excited about the new lab? If you think about, every company today collects data, and you collect the data because you want to get some value out of the data. And more, that value takes the form of a decision, of an action you can make based on the data. Whether to improve your business process, whether to improve your product, and so forth. And there are many, many examples, and you hear more and more this phrase that data is only as valuable as the decision it enables. And everything now is around decisions and action you can take on the data, starting with IoT. Let me just see. Financial application, high-frequency trading, manufacturing, unmanned vehicles, or virtual assistants like Alexa or Siri. So many of such applications. So now, if you buy that the data is only as valuable as the decision it enables, the next logical question is, what is a good decision? Well, that's not hard to answer. A good decision is a fast decision because faster decisions are typically better than slower decisions. A good decision is a decision on the fresh data, on the most recent data, rather than just on historical data, on yesterday data or the last week's data. And a good decision is on personalized information of the users, right? That's what it is, rather than on aggregate generic data. So as such, what we want to support this kind of decisions, we want tools which support real-time decisions on live data with strong security. By real-time, we are meaning about trying to decide in milliseconds. Live data means that we want to decide based on the current state of the environment rather than historical state. And strong security, we want to provide privacy, confidentiality, and integrity. And this is very important because it's not only, in many cases, security is required, but can lead to better services because it can lead to better decisions. And the reason is quite simple. if I guarantee the privacy of your information, if I guarantee that to you, you are going probably to be more likely to share information with me. And if you share that information with me, I can use to make better decisions. So now, this is how a typical decision systems look like, at least a system we have in mind during this talk. So on the right-hand side, you have environment. It's a bunch of sensors, actuators, and so forth, right? So it can be video games, robots, self-driving cars, or virtual assistants. And then what a decision system basically gets queries from this environment or these devices, and then renders back decisions, right? And there are many examples. I'm going to talk a bit, but one is to get a recommendation, right? What movie to watch, what things to buy, right? That's what it is. Now, the decision system consists of two parts. One, which takes the observation and the feedback, the log from these devices, and processes them in some intermediate data. So for instance, this can be a machine learning model, which performs recommendations. And then it's a second part, which is actually the decision engine, which uses this intermediate data to render the decisions. Right? That's what it is. Again, when we are talking about latency here, we have two feedback loops. One is in order of seconds or maybe tens of seconds, which updates the model, updates the intermediate data. Right? This is how fresh is the data on which you are going to make the decision. And then is a real-time loop, which is making the decisions based on this intermediate data. And here we are talking about tens of milliseconds or even milliseconds. Here are two examples of decision systems. The first is I alluded to, and it is classic machine learning pipeline. You collect logs from user logs or device logs. You use kind of machine learning algorithms, do training, you build a model, and then you push this model to a model serving system, and this model serving system is going to render the decisions to the query it gets. Another example, which I'm going to talk later in this talk, is reinforcement learning systems. And this is a pretty hot area in AI these days. But this reinforcement learning was at the basis, for instance, of was a key technology used by Google's AlphaGo, which, as you know, beat the Go champion, world champion last year. And basically what reinforcement learning system is doing is constantly observing and interacting with the environment. It gets a state of the environment, this observation, and based on this state, it renders an action. Like playing a game, you see as the observation gives you the position of the pieces on the board, and then the action is moving a piece. Okay? And this mapping between the observation of the environment and the action is called policy. So the main goal of this reinforcement learning is to compute a policy. And it's computing this based on the reward. If you made some moves in the game and you win, you have a positive reward on the moves you made. If you lose, it's a negative reward. Okay? That's in a nutshell. Now, I just told you that we want decisions which are real-time, are on live data, secure. But actually, this is not enough. We want a few other things from decisions. First, we want to be intelligent, right? We are talking here about complex decisions in uncertain environment, right? We are talking about fraud detections, detecting a cyber attack, medical diagnosis. These are the kind of decisions we are talking about. Second, we want the decisions to be robust. Think about the robots, self-driving cars. And robustness has different axes. You want to be robust, a system to complex noise. This is the input. for a car dash cam. And this is raining, snowing, and this is actually a sandstorm. Okay? So it's pretty noisy data. You want to be robust when some parts of the system fails. And also, you want to be robust in the presence of unforeseen inputs. All these algorithms are trained on a bunch of inputs to render certain decisions. But what happens if you present the system an input they never seen before? Okay? What do you want the system to do in that case? Right? Basically, you want the system to recognize that it never seen that input and take a conservative, fail-safe action. Like for a car, that will be slow down and stop. Okay? And finally, as the decisions augment the human's ability to make decisions, or make decisions on behalf of the humans, you want the decisions to be explainable. And that's kind of pretty natural, right? Think about even human interaction. If your friend or spouse makes a decision or take an action, which maybe is not what you expected, what is the first thing you do? You ask, why did you do it? You ask for an explanation, right? Like for instance, like if you have a machine learning algorithms looking at your X-ray and giving you a diagnosis, typically this is not enough. Why? Because if you go to your doctor and the doctor is giving you the diagnosis, the doctor is going to take your X-ray, is going to point on the X-ray and basically say, you see, that's what I'm going to use this diagnosis, because maybe this organ, it's a little bit, different size, different position, and things like that, right? If your mortgage application is rejected, you want to know why. And obviously, if a self-driving car gets you into an accident, you want to understand why. So that's, again, a very important aspect. So now, the RISElab goal, I told you that all labs at Berkeley have a particular goal. So RISElab goal is to develop open source platforms, tools, and algorithms for intelligent real-time decisions on live data. That's what we do. Next, I'm going to talk a little bit about the systems artifact we are planning to build. Again, we are at the very beginning. The lab started at the beginning of this year. So we are just a few months old. But the central software artifact is a secure real-time decision stack, or SRDS, for a lack of a better name, which is this open source platform to develop RISE-like applications, and targets emerging AI applications like hyperparameter search, reinforcement learning, and is secure from ground up. Now, this is the architecture we have so far, and this will change, so take it with a grain of salt. I'm going to briefly talk to you about the components, and then I'm going to zoom in on two systems which are more advanced, Ray and Pyren. Anyhow, so one central component of the architecture is what we call the RISE microkernel, and this is a minimalist execution engine, which is super fast, super scalable, and very flexible in terms of the computation model. And basically, the need for that is to factor out all the functionality which is implemented by many big data frameworks, right? They have some scheduler, some in-memory object store, some optimizer for their execution plan, and so forth. And the second component is ground. And Ground is a central repository for models, APIs, and has the APIs to capture the context in which the data gets used and produced. And this is very important because today the data comes in many different forms, is stored in many different storage systems, is processed by many tools, and is accessed by many people. So you want to track all this, everything, what happens. Right? You want to know who created a piece of data, when the data was changed, how was it changed. The same thing about the models. Okay? The next thing is what we call the time machine, and this is a cross-layer component which is supposed to allow you to replay the application, what happened at fine granularity. So why is that? If you have the ability to replay what happened, then many things, it can enable many desirable things. One, it simplifies the development and debugging. If you have a problem, you just replay it and to find the bug, right? To find the problem. It also helps with robustness because I can replace the algorithms again perturbed inputs. Noisy inputs. I can add some noise to the inputs, I can replace the algorithms, and I see how robust it is. It can help with explainability. Explainability really means what is in the input has generated a particular decision. Right? So if I have a lot of examples about the inputs and decisions, I can look about what is the difference, a minimal difference between the inputs which generated one decision versus the inputs which generated other decisions, right? The decisions like the mortgage application was approved versus was not approved. And based on that, I can see what factors in the input are determinant in rendering that decision. And security. You can confirm vulnerabilities, you can replay it to confirm vulnerability. You can patch the system, and then you can replay it to test for patches. And you can do compliance auditing, right? And finally, we have a bunch of application frameworks to make it easy to support different workloads, to support different kind of applications. And here we have Ray, Pyren, Clipper, and Opaque. Clipper is a model serving layer, and Opaque is providing additional security for Spark SQL, even when the operating system or the hypervisor are compromised. Okay? So next I'm going to focus on these two systems. First is Pyren, which we built, and we actually released their very initial versions. So what is Pyren? Pyren, it's parallel computing for non-CS people. Look, AWS makes things much easier than operating your own cluster. Okay? However, you still need to decide, in most of the cases, what type of instance you are going to use, how many instances you are going, what is the price, are they going to be spot instances or no spot instances, and so forth. Right? So in many cases, actually, you still need, you need DevOps to do it, right? And, everyone recognizes this challenge, and actually Amazon have released these kind of serverless systems like Athena, which is targeted for SQL, which fundamentally, you don't need to configure anything magically under the hood. When you run the query, it's going to resize the number of machines you are going to run the query on so that you get a good response time. Now, Pyren targets machine learning workloads. Okay? And the requirements is minimal setup overhead, minimal learning curve. So we want that everyone who can write a Python program, it should be able to use Pyren. Why Python? Because it turns out that machine learning, Python, is a lingua franca. Most of the algorithms are in Python. Okay? So, and this is not real time yet. It's we target minutes long jobs. But it's our first try. It's based on AWS Lambda and this Python Anaconda as a distribution, and Pyron is small, short-winged songbird, chiefly found in the New World. So how many of you knows about lambdas? Okay, so this is actually an Amazon, before going there. So what is lambdas? So lambda, it's an effort to make it much easier to manage your computation resources. The target application, so lambda is like a micro instance. It's a micro instance. You have 300 seconds at most, 5 minutes, up to 5 minutes you can use it. You have up to 1.5 gigabytes of RAM, and you are built in increments of 100 milliseconds. So it's pretty cool. So the goal of the workloads that targeted is that when you push data into Amazon, you want to process it, right? So that's what it is. It's like you push the data in Amazon, and when you get new data, you spin one of these lambdas with your program to process that new data, right? Doing some ETL or something like that. So that's kind of the idea, okay? He's going to be happy. Okay? So it's a pretty nice construct, okay? So we take that engine, and on top of it, we provide an easy-to-use API. Actually, it's very easy to use API. This is Python code, which basically here you have an array of 10 elements, and then you are going to add 1 to each of the element, and you do that in parallel. The map here takes this add one function and apply to each element in the list. So the output is 1, 2, 3 to 10. Right? Initially 0, 1, 2, 3 to 9. You add 1, it's 1, 2, 3, 4, 5 to 10. Okay? So it's very easy. Okay? So now what is behind, under the hood? So here how it works. On the left-hand side, your laptop. On the laptop, you are going to run this program. So what happens under the hood is that when you are going to have this map, you are going to serialize a function and the data and send them to Amazon, store them to S3. Then you invoke a Lambda, the Amazon Lambda, this micro server, which is 5 minutes long, up to 5 minutes long, 1.5 gigabytes RAM, or sort of. And this Lambda reads the functions and the data from S3, downloads the Anaconda runtime, the Python runtime, runs the code. Now, while this is running, actually it turns out that the program can proceed on this is what is called futures. Futures means that you start the functions, you don't wait from the result, you get a handle to that function, and then you can use later that handle to retrieve the results when it's ready. So you can do other things in the meantime. You are not blocked. Okay, so this is what you have, these results, and then you poll S3 under the hood. This is future results. When you say future results, this is what you write to get the results. And under the hood, this function polls S3 to see when the results are ready, the results produced by Lambda. When the results are ready, you are going to serialize them and put in S3 and then send back to the client. Okay? So this is what happens. Now, how well is working? Well, surprisingly well. It's like we tried quite a few machine learning applications. It's true, most of them are embarrassingly parallel. But still, one surprising thing is that both in terms of compute and data I/O, how much you read and write, scale almost linearly up to 3,000 lambdas. Now we are trying with 12,000 lambdas, and I'll let you know the results. We are still working on it. But this is pretty cool, right? You get actually 45 teraflops out of 33,000 workers. Okay? And the read-write, 80 gigabytes per second. Actually, so it's near linear scalability. So it's very cool. Actually, even Werner Vogels was impressed about that, so he tweeted about. Okay? Also showing some of the early graphs. So this is Pyren, right? Pyren, machine learning workloads, but they are coarse grained, right? They are still not real time. Yes, this is 22 February, so it's quite a bit. We improved since then. So now let me talk about Ray, which is one of the main projects. And what I'm talking Ray is not only the framework, but it also includes for now also this microkernel as a part of it. So Ray targets the reinforcement learning applications. And I mentioned to you this one of this example, right? So basically, these reinforcement learnings, again, what they do, they interact. You have an agent which observes and gets feedback from the environment, and based on that, is going to take some actions to maximize some reward. In the case of a game, the reward is winning or losing. Okay? The actions is moving the piece on the board. The observed state is a board state. Okay? Now, why is this a new kind of algorithms? They are what in AI, classical AI, you have what? And you have supervised learning and unsupervised learning. Now, this is closer to supervised learning. With supervised learning, you have an input and an output. For each input, you have a label. Right? Input label. With reinforcement learning, you don't have for each input a label, which is like an action. It's the equivalent of an action. So you get the feedback is delayed. So the inputs kind of are sparsely labeled. Why is that? When you play a game of chess or Go, when you move a piece, what is your reward? You don't know yet the reward until after, at the end, you won, whether you win or lose. So actually, in practice, when you do a task, take multiple actions before you know whether the task is successful or not. Okay? So that's the difference, right? It's sparse labels and delayed feedback, or sparse rewards. So let me give you an example here. So here it's a robot, and we use reinforcement learning to learn this robot, which is in a simulator, to walk or to run. So in this particular case, the environment, the observation in the environment is a position and of all the joints of the robot and limbs. The action is actuating these joints and moving these joints. The reward in this case, what you want to accomplish is, again, you want to run, but how you describe that to a program, or you want to walk. So here the reward has two components. One, do I move in one direction? Do I make progress in one direction? The second one, it's about the level of the head. The level of the head cannot drop under certain threshold. Why is that? It turns out if you don't put that constraints, one solution to this problem is for the robot to roll over. Okay? So here it's about, you see, there is an iteration, so it's iteration 0. So let me show you how it learns. So look at the iteration. So you see, every time you stop it, because the head, when you stop it, the head drops under that threshold, you see? You know, it starts to move a bit in one direction. Okay. Okay, so now he learned. So it's again, in this case, you don't know anything about, you only have a simulator, a physical simulator, and you don't know what are the action you need to take in order for the robot to run. So you don't know anything at the beginning, but you learn. So it's a very powerful method. This is also, it's used for Atari games. You heard about that, right? DeepMind at Google, right? To learn to play Atari games, expert level. Okay, so I have only 12 more minutes, so let me go into a deeper in Ray. So let's first start with what are the reinforcement learning requirements. First, you need to process and you need to observe to get the state of the environment. How you do that? Through sensors, right? And you have a bunch of sensors. You have video, you can have LiDAR, you can have microphones and so forth, right? So then you need to process each of them in parallel and in real time. Then, typically how these algorithms are working is that you do a lot of simulations until you are successful. Think about a game. How am I going to learn to play the game? How, right? One way, it's best just do random moves. And if you do, large number, if you play a large number of games, large enough, you are going to win some games just by chance. So now you are going to learn what moves you made which led to you winning the game. Okay? So you need to do a huge number of simulations. You need to do that. Then when you do simulation, we call rollouts. Then when some simulations finish, you take the results and you update the policy. And you want to update this kind of asynchronously. You don't want to wait for all simulations to complete, because some of the simulation can be very long. Like for instance, I can lose a game in 3 moves, or it may take forever to win, or it may end up in a tie. Okay? So it's a pretty asynchronous. And then often these policy updates, AGD, stochastic gradient descent, are implemented using deep neural network. DNN stands for deep neural networks, right? Which typically you execute on GPUs and CPUs. So really what you need flexibility. You need to combine neural network, planning, search, simulations. We need to support heterogeneous tasks which run on CPUs and GPUs. They have different durations. Implement different computations in parallel. And you need to have support fine-grained data and task dependencies. Performance, we want to support millions of tasks per second, or each task can take just a few milliseconds. So now we are talking about real time. And we want to be easy to use. Minimal changes to parallelize existing Python serial code. So you want to be able to take a Python code which implements the machine learning algorithms and to just parallelize it with very little changes, very few changes. Here is array architecture. Like many other systems, it has a driver and a bunch of workers which run tasks. It has also an object store, which is in memory object store. It's implemented in shared memory, so all the workers and drivers on the same machines can share the object. And on each node, you have a local scheduler. And this is because the scalability of the scheduler is critical, because remember, you want to schedule millions of tasks per second. So when the driver instantiates a task, the local scheduler tries to schedule it locally. Also, workers themselves can instantiate other tasks, so you can have recursive tasks. If the local scheduler cannot schedule the task locally because the node is overloaded, or maybe because the task accesses a very large object which is stored at a different node, you send that task to a global scheduler, we send it to which picks a node, sends to the local scheduler of that node, and which are going to execute the task. Also, one particular design of the array architecture is this global control store. So what we do, we take all the control state from the system and we put in a database. That's what we do, basically. Everything, where the objects are located, which tasks have been executed, what is their dependency, which tasks are in flight. Okay? So this makes the rest of the system very simple, because all the other components do not maintain state, which means the fault tolerance is easy. Any of these colored components fails, it's okay, because you start them again, and they go to the global control state store to get their state. Okay? And also, it's make it easy to build on top, because again, the entire state is in the database. It's much easier to build the web UI, debugging tools, error diagnosis, and so forth. Okay, so that's the system. How well is working? First of all, it's developed and deployed on AWS. Local task execution, a simple task, doesn't do much, is 300 microseconds. Remote task execution is around 1 millisecond. The object store read-write throughput is 6 gigabytes per second. How well it scales? This is basically how well it scales. On the x-axis is the number of nodes. On the y-axis, you have the number of tasks per second being scheduled. So you can see for 50 nodes, you have 1 million tasks per second. And the scale is basically linearly. How robust it is? This plot tries to answer that question. So on the x-axis, you have the number of nodes. You see this dashed line. So you start with 20 nodes, and then you go to 90 nodes at time 20 seconds, and you go to, 40 seconds or something. At 50 seconds, you go to 10 nodes, and then you go back to 20 nodes. And what you see here with blue is the throughput, the number of tasks per second in this experiment. So as you can see, once you have failures, the number of tasks is dropping, and then when you get more nodes, it's increasing. The reason that number of tasks you execute drops so much after the failures is that some nodes have failed. The results of those tasks on the nodes who have failed have been lost. So now we have to rebuild those results, to rerun the task who created the results on the nodes which failed. Okay? But that happens transparently under the hood, similar to Spark. Okay? And this is also useful to support spot instances, right? The spot instances will be taken away from you, depending of what is your bid. Ray also speeds up rollouts for policy gradient. The policy gradient is one of the main techniques used by reinforcement learning. And rollouts, remember, it's basically you simulate. This is what you do. You simulate, then you simulate the environment, you evaluate the policy, so play the game, you get the results, you simulate, and so forth. And this is doing this in parallel for CPUs, so the speed up is 1. So this is a baseline. Now the evaluation of the policy, if you remember, can be a complex, it's typically done using neural networks. So you can do that in GPUs. And if you do that in GPUs, you get an improvement, but not as much as you'd expect. You get 1.3x improvement. Why? Because actually the simulation, the CPU simulation, the simulation of the game is a bottleneck here. So it doesn't matter how faster you are going to be here, the GPUs, because the simulation is a dominant factor. So in order to do that, what you do, you are going to parallelize the simulations, and then you are going to update the policy from multiple simulations. You are going to aggregate that. And by that, you are going to, at least in this example, you get a 4x improvement. Okay? So this again demonstrates how Ray not only gives an improvement and it's flexible, but also can handle both CPUs and GPUs out of the box. Okay? And here we leverage P2 instances, P2 GPU instances. So in summary, RISElab goal is to develop open source platforms, tools, and algorithms for real-time decisions on live data with strong security. There are many challenges across AI systems, security, architectures, and of course, as a researcher, this is something we are very excited about. And we already started to release some software. It's still very early stage, but if you want to play, we'll be delighted. Just send us comments and feedback. But both Pyren and Ray are now open source and are available. So thank you.
Do you want to try to take 1 minute? Oh, wait,
no,
sorry.
we have, yeah. Do
you want to fit one question in? Or, we're good. Thank you, everybody. We'll be up here.
I'm here.
Oh, you are here. Okay.
Yeah.
Any questions? 1 minute. All right, here we go.
How are the policies modeled? I think one of the slides shows the model in the language of DNA or something.
DNN, deep neural networks. So you are asking what kind of other policies?
Yeah, how do you model the policy?
Oh, how do you model a policy? So a policy, the policy is a mapping between the input and an action and an output. So it's like a function. And in many cases, to model that, you use a neural network, right? Deep neural network, okay? So, and you can try with different structure of neural networks for different kind of policies. But that's a high-level idea.
So we talked about using the recursive method, but lots of things like in financial market, you cannot do lots of simulation. So how can you apply that?
Yeah, so the question is that, I'm talking about doing a lot of simulations, but in some cases you may not be able to do some simulations like in financial markets. I think that's fine, actually. There are reinforcement learning algorithms for the case of robotics. They don't, are not based on simulations, are based on the experimentations, right? What I can simulate, you also can try to do it in real world. The rate of learning, of course, will be slower. But this is, again, is not constrained to the simulation. But whenever you can simulate, you should simulate. That's the idea.
Thank you very much, Jan.
Thank you.